We usually think of a world this volcanic as a literal ball of liquid fire, but it turns out the gravity data from the Juno spacecraft suggests Io is actually quite rigid. This creates a massive mismatch between its solid interior and the record-breaking heat we see on the surface. If you look at the thermal data from December 27th, 2024, it's clear that something broke. We've known Io was active since the Voyager era, but Juno's recent flybys recorded an eruption that essentially redefined the scale of planetary volcanism. This single event released between 140 and 260 terawatts of energy. To put that in perspective, the previous record holder was a 2001 eruption at the Surt volcano, which topped out at about 80 terawatts. Even Earth's most violent modern events, like Mount St. Helens, only reach about 52 terawatts. So we are seeing an energy output that is 5 times larger than anything we've measured on our own planet. But interestingly, this wasn't just a single point of light. The GIRAM instrument, the Jovian Infrared Auroral Mapper, showed that multiple hotspots across an area of 40,400 square miles all flared up at the exact same time. It's as if the entire region was synchronized. And I guess the question here is, how do you get that much energy out of a moon that isn't completely molten? Researchers like Scott Bolton and Alessandro Mura have been looking at this data to figure out if there is a massive, interconnected network of magma reservoirs just beneath the surface. If these reservoirs are linked, a pressure change in one area could theoretically trigger a chain reaction across thousands of miles. It would explain why so much of the moon turned on at once, but just so we're clear, this isn't a global ocean of magma. The energy is massive, but the source is much more complicated than a simple liquid core. We are seeing a level of thermal power that our previous models simply didn't account for. But interestingly, if you look at the gravity science experiments from the most recent Juno flybys, they don't show a fluid world. If Io had a shallow global magma ocean, the moon would bulge and flex significantly under Jupiter's massive gravitational pull. But the Doppler shifts in Juno's radio signal tell a different story. The data actually supports a mostly solid mantle, which forces us to rethink how all that surface heat is being generated. So, we are moving away from the old idea of a magma ocean and toward what researchers are calling a lithospheric sponge. Essentially, the interior of Io is a solid, crystalline matrix, but it's riddled with interconnected pores and channels. Think of it like a giant rocky sponge where the water is actually molten silicate. This porous flow model explains how you can have a rigid body that still allows massive amounts of magma to migrate to the surface. And if you look at the thermal maps from GIRAM, you can see why this matters. A solid mantle with localized pockets of melt, what we call magma chambers, would usually produce isolated, sporadic eruptions. But the data shows these pockets are likely linked. In late 2024, when those multiple hotspots flared up across 40,400 square miles, it suggested that a pressure wave was traveling through this sponge over hundreds of kilometers. But just so we're clear, this is a very difficult environment to model. We are seeing a hybrid state that doesn't really exist on Earth anymore. On our planet, plate tectonics and a mostly solid mantle keep things relatively stable. On Io, the tidal heating is so intense that the sponge is constantly being squeezed. This squeezing forces the melt out of the mantle and up through the crust, which is why we see such a high density of volcanic centers without needing a completely liquid interior. It turns out, a moon can be solid and still be the most thermally active object in the solar system. If you look at the surface of Io, the most prominent feature is often Loki Patera, a massive volcanic depression larger than the state of Maryland. For decades, we weren't sure if we were looking at a solid crust or a liquid lake. But interestingly, the GIRAM instrument recently provided a high-resolution thermal map that essentially solved the mystery. It revealed distinct hot rings around the edges of the Patera, which is exactly what you would see in a massive, active lava lake. So the mechanism here is actually quite similar to what we see at Kilauea in Hawaii, but on a planetary scale. The lava in the lake cools at the surface, forming a dark, solidified crust. But because that crust is denser than the liquid magma beneath it, it eventually becomes unstable. It starts to founder and sink, usually beginning at the edges. As the crust sinks, it pulls fresh, glowing magma to the surface, creating those bright thermal rings that Juno detected. But I guess the question is, how deep does this plumbing go? The data from the microwave radiometer suggests these aren't just shallow puddles. The thermal signature persists deep into the subsurface, implying that Loki Patera is directly connected to those interconnected magma reservoirs we discussed earlier. And if you look at the circulation patterns, it turns out the lava might be overturning in a massive, predictable cycle. But just so we're clear, this isn't a calm process. The crustal recycling at Loki involves millions of tons of silicate rock sinking back into the mantle every few months. This process is a major way that Io sheds its internal heat. Instead of just erupting through a single vent, the moon uses these massive lakes as giant thermal windows to radiate energy directly into space. It's a highly efficient cooling system that keeps the interior from turning entirely to liquid, despite the constant squeezing from Jupiter. We usually expect a solid crust to act as an insulator, trapping heat inside a planet's core. But interestingly, the data from Juno's microwave radiometer, MWR, shows that Io has found a way to do the opposite. By probing several kilometers beneath the surface, the MWR detected that roughly 10% of Io's subsurface consists of still warm, unsolidified magma flows. These aren't just stagnant pockets. They appear to be part of a high-speed thermal transport system. So, if you look at the thermal signatures, it turns out these flows act like a car radiator. In a typical planet, heat moves toward the surface through slow conduction. On Io, the tidal squeezing is so intense that conduction isn't fast enough to prevent the moon from melting entirely. To compensate, the moon has developed a piping system where liquid rock carries internal heat directly to the surface at a massive scale. Essentially, the magma isn't just a byproduct of the heat. It is the primary cooling agent. And I guess the question here is, how much of this radiator is active at any given time? The MWR data suggests that while the visible volcanoes are the most obvious exit points, there is a vast hidden network of sill intrusions, horizontal sheets of magma just beneath the crust. These sills spread the heat out, preventing it from concentrating in a way that would destabilize the entire lithosphere. But just so we're clear, this cooling system is under incredible pressure. The microwave radiometer also picked up variations in the dielectric constant of the soil, which suggests that the chemical composition of these flows might be shifting as they cool. If these flows ever stopped moving, the internal temperature of Io would spike, likely leading to a global catastrophic melting event. But interestingly, the tidal resonance between Io, Europa, and Ganymede keeps the pump running, ensuring that this planetary radiator stays in constant motion. If you look at the fundamental physics of a moon orbiting a gas giant, the most important variable is the K2 love number. This is a dimensionless value that measures how much a body deforms in response to external tidal forces. For decades, we assumed Io's K2 value would be high, indicating a soft liquid interior that bulges easily. But interestingly, the gravity data from Juno's high-speed passes in 2024 and 2025 has essentially upended that assumption. The Doppler shifts in the spacecraft's radio signal, measured as it was tugged by Io's gravity, show a K2 value that is far lower than expected for a magma ocean. This tells us the interior is rigid. So, we have to ask, how do you generate the most volcanic heat in the solar system inside a solid rock? The answer lies in tidal flexing, because Io is trapped in a gravitational tug-of-war between Jupiter, Europa, and Ganymede. Its shape is constantly being distorted. But instead of the whole moon bulging like a balloon, the friction is happening at the microscopic level within that sponge mantle we discussed. And I guess the question here is, where exactly is that friction occurring? If the heat was generated deep in the core, the surface wouldn't look like this. But the gravity science data suggests the squeezing is concentrated in the upper mantle and the lower crust. This is what researchers call asthenospheric heating. Essentially, the rock isn't melting because it's hot. It's hot because it's being physically rubbed together by tidal forces. But just so we're clear, this rigidity is what allows the pressure to build up to record-breaking levels. If Io were a liquid ball, the energy would dissipate evenly. Because it is rigid, the sponge can hold on to that stress until it reaches a breaking point, leading to the 140 terawatt outbursts we've seen. The gravity data doesn't just tell us what Io is made of, it tells us why its eruptions are so violent. By being hard on the inside, Io is able to focus its energy into the spectacular displays we see on the surface. If you look at the collective data from the Juno mission, it's clear that our old liquid center models for Io were too simple. We've moved from a world with a global magma ocean to a far more nuanced architecture, a rigid, solid mantle that behaves like a lithospheric sponge. This discovery essentially changes how we calculate tidal heating for every other body in the solar system. By proving that a mostly solid moon can still radiate 260 terawatts of energy, we've shifted the habitable zone for tidal heating. So, the main idea here is that internal friction, not a molten core, is the primary engine of Io's chaos. The record-breaking eruptions and the interconnected reservoirs detected by GIRAM show us a world that is cooling itself through a high-speed subsurface radiator system. This isn't just a curiosity for our own solar system. As we discover more exoplanets orbiting closely to their stars, the new rules we've learned from Io will be the blueprint for understanding those distant volcanic worlds. And I guess the question now is what happens next. With the Juno mission entering its final phase in late 2025 and early 2026, the focus is shifting toward the long-term stability of these volcanic networks. We want to see if the Loki Patera hot rings are a permanent fixture or a seasonal cycle driven by Jupiter's orbital eccentricity. But just so we're clear, this is only the beginning of our reevaluation of Io. Upcoming missions like ESA's JUICE and NASA's Europa Clipper will eventually provide even more context for the Jupiter system as a whole. But for now, Juno has given us a look at a world that breaks the rules of geology. It turns out, you don't need a liquid world to have a liquid surface. You just need enough pressure and a very efficient way to bleed it off.